Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we are going to learn how to name cyclic alkanes with carboxylic acid as its main functional group. We're also going to take a look at how to name benzene rings with carboxylic acid as its main functional group. Also, we're going to look at how to name organic compounds that contains a double bond and a carboxylic acid as its main functional group. And we're going to take a look at how to name organic compounds that have more than one carboxylic acid as its main functional group. Last but not least, we're going to take a look at reactions involving the reduction of carboxylic acids. So let's go ahead and start. And so when you guys are trying to name a cyclic alkane that contains a carboxylic acid, we are going to treat the cyclic alkane as our parent chain, if you will. And so the carbon that's covalently bonded to the carbonyl carbon is always going to be carbon number 1. And very similar to the cyclic alkanes that we've discussed in prior chapters, since we know that this functional group is always going to be on carbon number 1 for cyclic alkanes, there's no need for us to indicate the locant or the carbon number that the carboxylic acid is covalently bonded to, just because it's always on carbon number 1. All right. And so kind of going around this ring, we have 1, 2, 3, 4, 5. So this is a 5-carbon ring. To name this 5-carbon ring, we're going to simply say cyclopentane. And so when you're naming these cyclic rings, the ending kind of changes. So we're not going to cross out the E and add the OIC. We're simply going to describe the functional group. So this is going to be cyclohexane, or I'm sorry, cyclopentane, carboxylic acid. Okay. So instead of saying cyclopentanoic acid, we're going to be using the full name of this functional group as the ending. And so since there are no substituents on this cyclic ring, we are done, and we're going to move on to the next compound. And so for this example, we have a carboxylic acid, so we automatically know that this is going to be carbon number 1. And so what we want to do is name the parent ring. In this case, we have 1, 2, 3, 4, 5, 6. And so this is going to be a 6-carbon ring, which is going to translate as cyclohexane. I'm using the A and E because there are no double bonds present in my ring. And very similar to what we did in the previous example, we're going to describe the functional group by using its full name. So cyclohexane, carboxylic acid. Now, we do have a substituent here in this example, and it's going to be a bromine. And so we're going to say bromo in place of bromine since it's a substituent onto the parent ring. Now we have to figure out the numbering system for this specific cyclic compound. And so we want to give bromine the lowest possible carbon number. And the only way that's possible is if we number our ring clockwise. So this is going to be 1, 2, 3, 4, 5, and 6. If you guys number it counterclockwise, you would the number that you would get for bromine would be 6. And so that's larger than 2. And so overall, this is going to be 2-bromo. So our answer is going to be 2-bromo cyclohexane carboxylic acid. And so since we are going to end, oh no, what's happening? Since we are ending our substituent with a letter, we're going to go ahead and put all of them together. And let's see here. So this is actually not necessary for you guys, just because this is not the full year of organic chemistry. But if you look at the type of bond that's being used to describe the relationship between carboxylic acid and this bromine, they're both pointing up. And so we didn't talk about the chair conformation for cyclohexane. And so with the three-dimensional structure of this cyclohexane, there's going to be something that's called axial and equatorial. And it turns out that the relationship between the carboxylic acid and this bromine, since they're both pointing up, we need to communicate to the reader that they're technically on the same side of the plane. And so this is basically what I'm referring to. So if I were to draw a chair conformation for this cyclohexane, so this chair conformation is basically looking at the ring on its side. Okay? And so the carboxylic acid is going to point up, and the bromine is also going to point up. And so if I cut this plane in half, both these groups, they're pointing on the same side of that plane. And so even though there's no double bond, technically we're supposed to put cis in front of 2-bromo to represent that both of these groups are pointing up. And so if you guys do not write cis in your exam, I'm not going to mark you guys off just because this is not the full year of organic chemistry. But I just thought I would throw that detail in. All right, so let's go ahead and talk about this cyclopentane. So I kind of gave away the parent name, but that's okay. So 1, 2, 3, 4, 5. So we have 5 carbons in our ring. And we see our COH. And so that would make this specific carbon, carbon number 1. And so we're going to go ahead and write the parent ring, the name of the parent ring, as cyclopentane. And we're going to go ahead and describe the functional group. So this is going to be cyclopentane carboxylic acid. Now it looks like we have a couple of substituents. We have a chloro or chlorine on carbon number 1. So this is automatically 1-chloro. And for carbon number 2, that's going to give us a methyl. And so I went ahead and numbered my carbons counterclockwise, just because it would give me the lowest number for the methyl group. If I numbered my carbons clockwise, the methyl would get a carbon number 5. And so the counterclockwise numbering system would produce the lowest carbon number for where that methyl group is going to be found on the parent ring. And so this is going to be 2-methyl and 1-chloro. Since we have 2 different substituents, we're going to organize them alphabetically. And so we're going to go ahead and put the chloro first. So that's going to be 1-chloro, and then 2-methyl, let me show my H here, and then cyclopentane carboxylic acid. And so since I'm going from letter to letter, I'm going to scoot this over. Remember that I do not need to indicate the carbon number for this carboxylic acid, just because it's always on carbon number 1. However, since I'm going from a letter to a number, I need to put a dash here. And then I'm going to scoot this guy over. And this would be the final name of this organic compound. All right, so looking at our last example, we have this cyclic ring, this cyclic alkene. Counting the number of carbons, we have 1, 2, 3, 4, 5. So this is our carboxylic acid, COOH. And so since my carboxylic acid is found on this carbon, this is going to be carbon number 1. And so I will say that this is cyclops. What is this? So the name of the parent ring is going to be cyclopentane. And then I'm going to describe my functional group, carboxylic acid. So now that I've described my parent ring and my functional group, I'm going to go ahead and describe my substituents. And so it would only make sense for us to number our ring counterclockwise. That would give the chlorine the lowest carbon number. So this is going to be carbon number 2. So bromine, since it's on carbon number 1, where that carboxylic acid is found, this is going to be 1-bromo. So for carbon number 2, we have a chloro. So we're going to say 2-chloro. Notice that we have 2 different substituents, chlorine and bromine. So we're going to organize them alphabetically, such that the B comes first before C. And so this is, I need to move this down. So our name is going to be 1-bromo, and then dash 2-chloro. And I'm going to go ahead and scoot everything to the right so that the main organic name of this compound is going to be one word. And so this is how we're going to name our cyclic alkanes that contains a carboxylic acid as its main functional group. And so I do want you guys to notice that the ending, the suffix, is not going to be oic acid. The oic acid is going to be reserved for the straight chains. And so there's just little differences here and there between cyclic or straight chains. Now we're going to go ahead and take a look at how to name benzene rings with carboxylic acid as its main functional group. And so if you guys recall earlier, if you have a benzene ring with a carboxylic acid as its main functional group, the common name is going to be benzoic acid. So this whole item that I've circled is going to be named benzoic acid, such that this carbon that it covalently links the carboxylic acid to the ring is going to be carbon number 1. And so let me just put a circle around here more permanently, and I'm going to write benzoic acid. And that's going to represent the parent name. And so the only thing that I need to name is my substituents, which in this case happens to be 2 chlorines. And so I'm going to go ahead and name this or number this clockwise. If I were to number it counterclockwise, I would get numbers that would be higher compared to numbering it clockwise. Oops. And so this carbon is going to be carbon number 2, carbon number 3. So it looks like I have A2-chloro, a 3-chloro, and since they're both the same substituents, I can combine them together and describe this answer as 2,3 dichloro. And then the name of my parent, what's happening here? The name of my parent chain is going to be benzoic acid. So 2,3 dichloro benzoic acid. Once again, I'm omitting using placing the carbon number 1 in my name to describe the position of the carboxylic acid, because the carboxylic acid for any rings or straight chains is always going to be carbon number 1. Okay. My screen is freezing. It's weird. All right. So let's go ahead and name this compound. So here I have my benzene ring with my carboxylic acid. And so this whole area is going to simply be named as benzoic acid, with this carbon as carbon number 1. And so it looks like we have 2 substituents. We have 2 bromines. And so we have to number our carbons in such a way that both of these bromines would have the smallest value. Now if I were to number it clockwise, I would get 1, 2, 3, 4, 5, 6. If I were to number it counterclockwise, I would get 1, So this is going to be 1, 2, 3, 4, 5, 6. So looking at our numbers, I have 3 and 5. I also have 3 and 5. And so because I have 3 and 5 for both these bromines, it actually doesn't matter which way I number my carbons on my parent chain. And another way that you guys can recognize this is the symmetry of this molecule. And so if I were to draw a red line, and for now I just want you guys to focus on this segment of the molecule. Notice how it's symmetrical. Both of them have the same substituents, and you can fold it in half and they will overlap. And so little clues like that will inform us that it doesn't matter which way we're going to number our carbons on the benzene ring, because we will end up with the same number. All right, so let's go ahead and name this. This is going to be 3-bromo. This is going to be 5-bromo. And so since we have the same substituent, this is going to be 3, 5 dash dibromo benzoic acid. And that would be the name of this compound. Okay. All right, so we're going to go ahead and go through our last benzene ring here. So this whole section is going to be our benzoic acid. We know that this is carbon number 1. And so just by looking at the structure, I know that if I number it counterclockwise, this chlorine would get its lowest possible carbon number. And so this is 1, 2, 3, 4, 5. And so since I have 2 chlorines on carbon 2 and carbon 5, I'm just going to say 2, 5 dichloro benzoic acid. And we're done. Why is my screen? So my screen is freezing. In other words, I can't move my screen unless I go back out and go back in. All right. So the last for this last slide for naming carboxylic acids, we're going to take a look at how we're going to name carboxylic acids with a double bond, and organic compounds that have more than one carboxylic acids. All right, so let's go ahead and take a look at this structure on the top. We know that this is carbon number 1 because it has my carboxylic acid. And so in terms of identifying my longest carbon chain, I can go straight across 1, 2, 3, 4, 5. So this is going to be pent. Now, if you look, I have a double bond in my parent chain. And so if I have a double bond in my parent chain, then that means I need to use pentene. But since I have a carboxylic acid, then I'm going to follow my rules as always, and I'm going to cross out that last E and put in the oic acid. And so here I have pen-10 oic acid, where the En represents the double bond, and the oic acid represents the COOH, or the carboxylic acid. Now, we don't need to indicate the carbon number of where the carboxylic acid is bonded to, or where it's located on the parent chain, but we do need to tell the reader where this double bond is on the parent chain. And so that means we need to add a number in front of our prefix pent. And so if we number our carbons from left to right, right to left, we have 1, 2, 3, 4, 5. So it looks like on carbon 2, our double bond starts. And so we are going to indicate to the reader that the double bond starts on carbon number 2. It looks like we have a substituent, which is a chlorine group, and it's on carbon number 4. So this is going to be 4-chloro. And so overall, we can go ahead and combine these two pieces that we've written out together. And so we're going to go ahead and say that we have 4-chloro dash 2 dash pen 10 oic acid. So 4-chloro dash 2 dash pentanoic acid. Okay. And so what we're doing is we are communicating to the reader what carbon number that double bond, where that double bond is located. All right, so let's go ahead and take a look at the next one. This one's a little simple. And so once again, we're going to figure out the longest carbon chain that contains the carboxylic acid. So we have 1, 2, 3, 4. So this is a 4-carbon compound. And therefore, we're going to go ahead and put in bute as the prefix to represent a 4-carbon compound. Now, typically, we put butane, but if you look, we have a double bond. So we cannot put butane, we have to put butene. And following our rules of naming straight chains for carboxylic acids, we're simply going to cancel out the last E and then add in the oic acid ending. So this is going to be butanoic acid. And so we need to tell the reader where that double bond is going to be located in our carbon chain. And so if we take a look at our numbering system, here we have 1. Remember, carbon number 1 is always on the carboxylic acid. 1, 2, 3, 4. And so it looks like our double bond starts on carbon number 2. And so we're going to put a number in front of bute, and this number is going to tell us that number is going to tell us the carbon number that the double bond is found. All right. So looking at our last two examples here for naming carboxylic acids, we have succinic acid and malonic acid. And so the succinic acid and malonic acid are just common names. And so if you wanted to name these compounds using the Iupac nomenclature, our first step is to find the longest carbon chain that contains our carboxylic acid. So we have 1, 2, 3, 4, 1, 2, 3. Okay. And so we know that we're going to be using bute for succinic acid, and we're going to use prop for malonic acid. Now, since we have a carboxylic acid, or actually, let me take a step back. So looking at the skeletal structure, looking at both skeletal structures, notice that they're all single bonds. And so I'm going to say butane, propane. Now, looking at the number of functional groups, looking at the number of carboxylic acids, here we have 2. And so here in this case, we're going to have to tell the reader that we have 2 carboxylic acids. And the way that's done is that you do not cancel out the E, you just add on. You just say butane dioic acid. And then this is going to be propane dioic acid. And so I'm going to highlight the word di here in pink. And so what I highlighted basically represents 2 carboxylic acids. And that would be it. So typically we would have to indicate the carbon number on the parent chain, but since we know that that carboxylic acids are found on the ends of a carbon chain, there's really no point. And so if you wanted to, you can put in like 1,4 butane dioic acid to communicate to the reader that the carboxylic acid is found on carbon 1 and carbon 4, or carbon 1, carbon 4. In this case, it's really unnecessary because we know that the carboxylic acids are going to be found terminal on the parent chain. All right, so that's pretty much it in terms of naming carboxylic acids. And so I just want to take a look at one specific reaction for carboxylic acids, which is the reduction of carboxylic acids. And so this is something that I discussed in prior lecture videos. So this idea of oxidation reduction. Oops. And so what we're mostly looking at is this part right here. So you guys have seen this specific diagram before in prior lecture videos. And so now that we know what the carboxylic acid functional group looks like, based on what we discussed in prior lecture chapters or lecture videos, these carboxylic acids can undergo reduction to produce aldehydes. And since carboxylic acids are terminal functional groups, it makes sense for the functional group that it's going to produce after reduction has occurred is also a terminal. And the only terminal functional group is aldehyde besides the carboxylic acid. And so basically wherever you guys see a carboxylic acid, you guys are going to convert it into an aldehyde. So looking at this first example, this is our COOH, our carboxylic acid. And so if we reduce this, in other words, we're adding in hydrogen somehow, we get an aldehyde at the very end. Okay, and so that would be the product. Now looking at the next compound, here we have a carboxylic acid. And so everything else pretty much stays the same. The only thing that we're doing is that we're converting this carboxylic acid into an aldehyde. And so I'm using H to represent reduction. Why? Because I'm gaining more connections between carbon to hydrogen when reduction occurs. And so here, for our last example, we have this benzene ring with 2 bromines. So the bromines are not touched. However, wherever we see the carboxylic acid, that just turns into an aldehyde when a reduction reaction occurs. So reduction of carboxylic acids, pretty simple. We're only going in one direction. We're going from carboxylic acid to aldehyde. Now, obviously, if we're talking about oxidation, then we're going to go ahead and take this aldehyde and convert it back to a carboxylic acid. Remember, with oxidation, we're decreasing the connection between the carbon and the hydrogen, and we're increasing the connection between carbon and oxygen for oxidation. So this connection is destroyed, this connection is made. Alright, so that's pretty much it for this lecture video. We covered many different ways on how to name carboxylic acids, and we looked at the reduction reaction of carboxylic acids.